Today we're going to start dealing with Chapter 11 with radical expressions. And radical expressions really have to do with dealing with square roots and simplifying them. And you'll notice that that's actually this focus of this very first section. So we're going to spend some time today kind of going over some basic guidelines of how things work. And then we're going to talk a little bit about kind of the shortcut method that I use. So let's take a look at our first couple pieces here. First of all, to simplify a radical, if I have two numbers multiplied together underneath a square root, I can actually simplify them by separating them. Sometimes that's helpful if you can realize that there's what's called a perfect square inside of there. Now, perfect square are numbers that you would get when you square a number. So like 1 squared is 1, 1 is a perfect square. 2 squared is 4, so 4 is considered a perfect square. And I could keep going on and make a humongous list here if I wanted to of stuff that would never end. So being able to recognize these perfect square roots is kind of helpful. So on something like example number 1, if you notice that you have 54, I know if I'm thinking about perfect squares that could be 6 times 9. And if I separate those into two separate square roots, this part would be equal to 3. I can't do anything else with this one, so it would be 3 square root of 6. Now that's what's called simplifying. Now I want to show you something that may be a little bit different, but this is actually the way that I solve them. I take whatever number I have. This one happens to be 54, and then I'm going to use this factor tree method. The factor tree method is something that you probably did in elementary school. So what number times this number could give you 54? So if you did 9 and 6 like we just started with, that's great, but neither one of those numbers are prime. I can break 9 into 3 times 3. Those are both prime. I just kind of tend to circle my prime numbers. 6 breaks down into 2 times 3. So I want to show you one other method besides this here of being able to solve it using this perfect, or using this factor tree. So first of all, if I were to look, I put them in order underneath here from smallest to largest. So there's 1, 2, and then there's 3 3s. This is actually called the prime factorization. So, because these are all prime numbers. Now I look for a pair. And this is the story I always tell. So I look for a pair. A pair is like a date to a dance. These two would be a date to a dance, perfect pairs here. But 2 and 3 don't have any pairs, so they don't have a date to the dance. So if I were to pull this out in front, 3 times 3 is 9. The square root of 9 is 3. So basically the rule is for every pair that you get underneath here, it can be pulled out once in front of the square root. So I have a 2 and a 3 that don't have a date to the dance that are left underneath, which gives me 6. Now notice this answer is the same one I got the other way. Sometimes people are much more comfortable using kind of this, using the factor trees and going down to perfect square or going down to prime factors. Now, you do have to make sure that if you use this factor tree method, that you factor it completely. That means that these numbers out here, when you're done, the only way you can get those numbers is that number times 1. So let's try this again. Let's try it with some real numbers here. So first of all, here's a couple examples that we're going to look at. The first one's the square root of 192, and the other one's 100 x to the 5th, y to the 3rd, the square root of all of that. So we're going to start out just the same way I did in that last one. I'm going to take my 192, and I'm just going to start factoring it. Now the only thing I know about 192 is at least it's even, which means that 2 will go into it. So 2 and 96 multiplied together will give me 192. That's prime, and I'm going to keep breaking this one down. So this one, when I look at it, I think 3. So 3 is going to go in there 32 times. 32 would be 4 times 8, and 4 is 2 times 2. 8 is 2 times 4, and 2 times 2. So if I look at this one, I actually have a lot of factors in this one. So there's 1, 2, 3, 4, 5, 6 2's, and a 3. So when I go back here to rewrite this, there's going to be 6 2's, and a 3. Now remember, we look for our dates to the dance. So here's one pair, here's another, and here's another. So there are 3 pairs of 2's. For every pair, you write it in front once. So there'd be 3 2's, and the 3 doesn't have a date to the dance, so it stays underneath. So 2 times 2 is 4, times 2 would be 8. So this is 8, square root of 3 is the most simplified piece. Okay, let's try this one over here. On this one, my big thing to factor really is the 100. I'll show you what to do with those letters when we get there. But if I do my 100, 10 times 10, and each of those break into 2 times 5. So I have 2 2's and 2 5's. Now if it's x to the 5th, that means you've got 5 x's. And the y to the 3rd means you have 3 y's. Okay, now we're looking for pairings. Here's a pair. Here's a pair. Here's another pair. Here's another pair. So there's a 2, a 5, x, x, and y that have partners, and then x and y that don't. Now the big thing in this is the 2 and the 5 can come together to make a 10. X times x is x squared, and then y. And then x, y remain underneath. So this is my most simplified version. Now there is quite a lot in this section that we're going to have to deal with. So we really have to look at our pairings, and we have to look at how we simplify things. So let's take a look at the next one. Okay, now these are already separated. And they have, this is just my fancy multiplication symbol I had to type, so wanted it to look neat. Now if it were me, I would actually just take these and start factoring them right underneath. So that 12 breaks down into 2, 2 and 3. 32 breaks into 4 and 8. And 2 and 2. Now, if I were going to put these together, I would actually go for putting them all underneath one square root, all in order. Oops, that's a terrible line. Let's try that again. No guarantee it'll be better, but we'll try here. Okay, so 2 is the smallest number. I would count up how many I had all together. So if I counted up how many I had, 1, 2, 3, 4, 5, 6, 7. So 7 2's. And 1 3. Now one of the things that's nice about this is that if you go to actually looking at this, much easier to make the pairings and do that if you put them kind of all together. Now I'm going to grab my red so I can do my little hearts here. So here's a pair, here's a pair, here's a pair. So 3 2's in front, a 2 and a 3 left underneath. So 2 times 2 is 4, times 2 would be 8, and underneath we'd be left with 6. So 8 square root of 6 is our final simplified answer. Now, we also have to deal with this idea of division. And so if you have something that looks like a fraction here, I can separate them into two, pieces where you have a square root in the top and a square root in the bottom. The only thing that you have to remember is the square root in the bottom has to be gone when you're all done. You can't leave a square root in the bottom. It's one of those rules that they don't let you do. So in this one, if I went and looked at these, first of all, I know 16 and 25 are both perfect squares. So that means that if I go through and separate them, square root of 16 is 4. I know that's a perfect square one. Square root of 25 is 5. And this would be my final answer. Now in this one, I can kind of see the same thing. The 144 is a perfect square, and I don't know if you realize it either, but p squared is actually a perfect square as well. It's p times p. And 36 is a perfect square. So on the top it's going to be 12p. On the bottom, square root of 36 is 6. So 12 divided by 6 is 2, so it's going to be 2p. Okay, let's take a look, see if maybe we can get another couple examples in here. Now, I mentioned before that you can't leave a square root in the bottom. To get rid of it, it's called rationalizing. So you have to usually multiply to get rid of it. So if I was looking at this example, if I didn't want that square root of 2 in the bottom, I'd have to multiply the top and the bottom by square root of 2. Because I want you to watch what happens. On the bottom now I have two 2's. I'm just going to take those both and put them underneath 1. And on top I have 1 square root of 2. And this right here is a pair. So because there's a pairing of 2's here, this is just going to be 2 in the bottom. And actually, most of the time you see this, they'll probably drop the 1 in the front of the square root of 2 because they assume there's a 1 there whether you write it or not. Now this is called rationalizing. I've been able to multiply the top and the bottom by the same number, usually by whatever the square root is in the bottom. And I want to do it so I get rid of the square root in the bottom. That's my ultimate idea. So, let's see if I can move this down just a little bit here. So if I'm looking at this one, square root of 5 is what I need to get rid of. So multiply at the top and the bottom by square root of 5. So this will be 2 square root of 5. And now on the bottom there are 2 5's underneath the square root. This one and this one. So now there's a pairing in the bottom. So it'll be 2 square root of 5 over 5. That's my final answer. Now this one's a little more challenging. Now let me just rewrite this so it actually looks a little bit normal. It starts out like this. And my job is going to be to first of all separate those square roots. Because I got to get rid of the square root of 10 that's on the bottom. So I'm going to multiply the bottom and the top by the square root of 10. So on the top, those are really all going to be underneath, and there's not going to be any simplifying I can do. So I could make that 70m, because I could multiply that part together. Now on the bottom, I have 2 10's. So there's my pair. So it'll be the square root of 70m over 10. And remember, the idea with this one is to be able to get rid of the square root in the bottom, which I've done. This is our final answer.